So my field of research is collider physics. I'm using the proton-proton collisions from the Large Hadron Collider at CERN to study the standard model of particle physics. The standard model is our current best theory of how nature works at a very fundamental scale. But particle physics is currently in a very tricky situation. We know from astronomical observations and from internal theoretical issues that the standard model is not the final theory. But so far in all the measurements that we've done at the LHC, there was no direct evidence of new physics. So we have a theory that fits so far all the experimental data, but we know the theory is incomplete. For my thesis, I studied the Higgs boson to see if the properties of the Higgs boson agree with the standard model or if there are some deviations. Now, studying the Higgs boson is interesting for two main reasons. First, it's the particle that we know the least of experimentally. We only discovered it in 2012 and we're now starting to study it. And second, the Higgs really sits at the heart of the standard model. So it is deeply connected to all these issues that we have with the standard model itself. When I started my PhD at the end of 2017, the Large Hadron Collider was just getting into the final phase of its second operational run, which lasted from 2015 to 2018. And during that time, the ATLAS experiment collected the largest proton-proton collision dataset ever available. And in this dataset, there were 8 million Higgs bosons to analyze. So I wanted to use this large dataset to study very rare processes of the Higgs boson, which are particularly sensitive to new physics. And in my case, I wanted to look at Higgs bosons that were produced with very high energy. Because most of the time, if you produce a Higgs boson from 2 protons, the Higgs boson will be produced at rest and then it will decay. In a few cases, however, the Higgs boson will get an additional kinetic energy. And these cases are very interesting because we expect new physics to be more prominent there, which makes it interesting to look at these sort of events. Reconstructing Higgs bosons with a very high kinetic energy is very tricky to do. So together with my colleagues at CERN, we developed a novel analysis strategy to be able to reconstruct the Higgs bosons from the signatures of the decay particles in the detector. So the result of my thesis is a measurement of the production cross-section of the Higgs boson as a function of its energy. So the production cross-section is the probability of producing a Higgs boson at a certain energy. And especially the 2 last bins we could measure thanks to these new reconstruction algorithms that we developed. Now, unfortunately, you see on this plot that the data that we took in the black points agrees with the standard model predictions. However, we could use this measurement, which is the most precise measurement of the Higgs boson production cross-section in this particular decay mode to date, to set stringent limits on how new physics will look like if it couples to the Higgs boson.